So this part is a little more important, and also there's really no math. So some of you will appreciate that. So there are different types of crystalline solids. And they're grouped based on what are the particles that make up that solid. So I'm going to talk mostly just from this chart, and then we'll go through the slides that have all the details. So crystalline solids. We can have a crystalline solid made up of molecules, of ions, or of atoms. Those are the particles that make it up. If we have molecules as our units, then that's called a molecular solid. If the units are ions, it's called an ionic solid. And if the units are atoms, it's called an atomic solid. Can you see? We're not trying to trick you here. An atomic solid is made up of atoms, right? A molecular solid is made up of molecules. Characteristics of these, well, molecular solids, what holds two separate molecules together? We just learned about that in chapter 12. Intermolecular forces. Are those really strong compared to bonds? No, they're not very strong. So these are held together by intermolecular forces, and as a result, these have relatively low melting points. A lot of these things will be liquids at room temperature. Ice is an example of a molecular solid because the individual particles are molecules of water, right? Ionic solids have ions. So you can't just have a bunch of negative ions or positive ions. You have to have positive and negative together. Overall, it has to be a neutral compound. So we've got these formula units where you've got cations and anions, and how many of each is going to depend on their relative charges. Right? Sodium chloride, you've got one sodium for every chloride. So these are going to be held together by ionic bonds, that force of attraction between the oppositely charged ions. Ionic bonds are very strong, and so ionic compounds tend to have very high melting points. You think about salt, right? Does salt melt? You ever seen salt melt? Probably not, because you have to get it like crazy hot. It will melt, but at like thousands of degrees, right? So high melting points for those. And then we have the atomic solids. So here, these are just composed of atoms. And this is actually a much smaller group than the molecular solids or the ionic solids, even though it does have its own 3 subgroups. And those depend on how the atoms are held together. We can have a non-bonding atomic solid. Here, those atoms are just held together by dispersion forces. They're not going to have dipole-dipole forces or hydrogen bonds because they're atoms, they're spheres, they're not polar. All they have are dispersion forces. And dispersion forces are very weak, and so these are going to have very low melting points. And in fact, the only examples of non-bonding atomic solids are the noble gases, neon, argon, etc. And you have to get them extremely cold to make them freeze. Another kind is the metallic atomic solids, and as you might have guessed, this is metal atoms, right? So metal atoms are held together by metallic bonds. We talked about that very briefly, about how the metals don't hold on to their valence electrons very well, and so the electrons just kind of go out and around, and it's a little bit like kids being let out to play in the neighborhood, and the fact that there's all these children running around kind of keeps the neighbors together because they're kind of keeping an eye on everybody's kids, right? So metals are going to have a variable melting point. Some melt at very low temperatures, like mercury is a liquid at room temperature, but some of them melt at very, very high temperatures. So that varies a lot. And then we have network covalent solids. So here we have atoms that are held together by covalent bonds. So these are also going to have high melting points because, again, the forces that hold these atoms together are very strong. Quartz is an example of a network covalent solid. So, info about molecular solids. Some molecular solids can crystallize in different structures. So made up of the same molecules, but they went into different types of unit cells. And those are called polymorphs. Those can have different melting points and solubilities compared to each other. And this is really important in pharmaceuticals because different polymorphs often have different physiological activities. And the example given here is kind of interesting. This is chocolate. So there are actually 6 polymorphs, 6 different types of crystalline structures for chocolate. And which one you end up with depends on how you treat the chocolate. How fast you heat it, how high, how quickly you let it cool down, etc. And they're going to have different characteristics. So, the type 1 melts at 17.3 degrees. So it's 22.5 in this room right now. So that form of chocolate would be a liquid at room temperature. Not great for a candy bar. As we go through these, their melting points get larger. And this type 5 is considered the best. That has a melting point of 33.8. So that's going to be a solid at room temperature, and it's not going to melt in your hand, but it will melt in your mouth. So there's a commercial. They melt in your hand, not in your mouth. They melt in your mouth, not in your hand, sorry. So I'm not in advertising. Melts in your mouth, not in your hand. And that's kind of a big deal because it's not nice when the chocolate melts all over your fingers, right? And so this has to do with how it was made. And so then there's different descriptions. So these all melt in your hand. This is going to melt in your mouth. This kind, you can't make it from melted chocolate, but if you leave chocolate number 5 for a long time, it can form into number 6. And that's what this one looks like. So, maybe there's a forgotten candy bar from Halloween in the back of the cupboard or under your son's bed. Could happen. And you're like, well, hey, he obviously doesn't want this, so I'm going to eat it, right? I'm cleaning his room, I get the candy bar. And you open it up, and it looks like this, and you're like, ew, is that mold on the chocolate? No, that chocolate is perfectly safe to eat. That's called bloom. And it's just something that chocolate does. It's not any other substance or growth, it's just the chocolate. Now, is that desirable? No, it isn't. But you can eat it. Okay, so you have permission to eat the old Halloween candy. Any questions? Ionic solids, again, composed of ions, and as this says, more on ionic solids later. Non-bonding, so the non-bonding ones, noble gases, metallic atomic solids, these are the metals, and this is an illustration of that metallic bonding model where each of these atoms has valence electrons that are kind of loose, and so they'll travel around. And so this holds the atoms together. Then we have network covalent solids. Examples of this are diamond and graphite, also silicon dioxide. The crystal structures here are not just based on the size of the atoms, because these atoms are covalently bonded together, and so the crystal structure is going to depend on the geometry of those covalent bonds. These are going to have very high melting points, and they do not form closest packed structures. So this is the kind of question you should be able to answer. What type of atomic solid is Au? Metallic, right? How do we know that? Well, we find Au on the periodic table, and even if we don't remember that it's gold, we see that it's in there with the other metals, right? It's a metal, so this is a metallic atomic solid. And then here it says, which solid would you expect to have the highest melting point? So let's think about what kind of solids do these make? MgO. So we had molecular solids, ionic solids, and atomic solids. Is this composed of molecules, atoms, or ions? If we were naming it, what kind of a compound is it? Ionic, right? Because we look at the first element. The first element is magnesium. It's over there. Magnesium's a metal. This is metal, non-metal. This is ionic. So I'm just going to write that down. That's an ionic solid. How about I2? Molecular, because this is a diatomic molecule. 2 iodine atoms, so this is molecular. And krypton. This is going to be an atomic solid, and specifically a non-bonding. So if we want to know which of these is going to have the highest melting point, we're going to think about what's holding these solids together, which one has the strongest thing holding them together. So ionic solids are held together by ionic bonds. Molecular solids are held together by intermolecular forces. And atomic non-bonding solids are held together just by dispersion forces. So we got dispersion forces. We've got intermolecular forces, which can vary. And we've got ionic bonds. Which of those is the strongest? A, ionic bonds. So magnesium oxide is going to have the highest melting point. With these two, intermolecular forces and dispersion forces, I wouldn't make you choose between those two, because that just involves a little bit more thinking, right? One thing you can do is just look at the periodic table, and that shows the state at room temperature. Iodine has a black letter, so it's a solid. And what does krypton have? Red. That means it's a gas. So which one has the higher boiling point between those two? The gas has the lower boiling point. Yeah, it's a little hard to think about, isn't it? So we start with a liquid, and then we're heating it up. And the first one to turn into a gas is the lowest boiling point, and the last one is the highest boiling point. Yeah, it's kind of hard to think about. So I wouldn't make you do that. But this would have a higher melting point than krypton. Any questions?